So in the previous class we discussed about the photoelectric effect and what are the observations given by Hertz, Leonard and also Hallwachs. So three observations we discussed yesterday, and today we'll start experimental study of photoelectric effect. So how we can study the photoelectric effect experimentally, and what are the observations or conclusions or results from this experiment we have to study in today class. Now for this I'll go a simple diagram used for experimental setup. So in this setup there will be one evacuated glass tube. You should take one evacuated glass tube inside completely vacuum, and also side there is a window. It is one evacuated glass tube, and in which we are providing a side window to this glass tube. Generally this side window may be made of glass or quartz. So it is a side window made of glass or quartz. This is a glass tube which is completely evacuated, and one end of the glass tube we are providing an electrode, so which is coated with a photosensitive material. So generally photosensitive material means which emits electrons when radiation falls on the metal. So it acts like a cathode, and other end we are providing a collector or anode. Generally with respect to cathode, anode having a positive potential, so we are using a symbol A. So one end of the glass tube we are providing a cathode, and other end we are providing a anode. So here cathode and anode both are connected to one reverse switch, so which is also called a commutator. So here both cathode and anode are connected like this. So here I am connecting a anode to one terminal of the reverse switch, and anode also connected to the terminal of reverse switch like this. So it acts like a commutator. So the purpose of this reverse switch, with respect to cathode, we can maintain the potential of the anode positive or negative. Thus we are choosing one reverse switch like this. So cathode and anode both are connected to the reverse switch or commutator. Next here, for measurement of the applied potential, we are using one voltmeter. So here I am choosing a symbol as V. So the purpose of the voltmeter in the circuit for measurement of applied voltage or applied potential difference, and also one microammeter is connected for measurement of the photo current. So how much current is flowing through circuit if you want to measure, so there is a microammeter. So here I am using a symbol mu A, microammeter. Next, for applying a potential difference, so we need to connect a battery, and also for potential divider like a rheostat we should connect. Here I am connecting a rheostat or potential divider. So we can use the symbol as RH. So the potential divider or rheostat, I am using a symbol as RH, and also one battery will be connected here. So in case of the DC source, bigger terminal represents a positive and a smaller terminal represents a negative. So it is so if you required, we can connect one plug key also, which will act like a on and off switch. So K represents a plug key, and here it is a battery which we can apply the required potential difference also minus. And here this micrometer terminal, here I am connecting to the rheostat upper terminal. So it is rheostat upper terminal, and here it is equal to G, that indicates a glass tube. So in the diagram, so G represents one evacuated glass tube, and there is a side window. So this will be nothing but side window, W we can write, and the C indicates a cathode, and A represents anode. So both cathode and anode are connected to one reverse switch. Here I am representing symbol as S, reverse switch. So the purpose of the reverse switch, whenever if you want to apply potential of the anode positive, we can apply, and negative or zero we can apply by using this commutator or reverse switch. For measurement of the applied voltage, we are using one voltmeter. For measurement of current flowing in the circuit, we are using one microammeter. Next one, potential divider or rheostat. So we can apply various potential differences by using this rheostat also. One rheostat, one battery, and one plug key also connected. So plug key act like on and off switch. So it is a experimental setup generally. For example, first I am choosing a radiation like ultraviolet light or visible light. A radiation of the suitable frequency is allowed to pass through the window of the glass tube like this. So it is a radiation of a suitable frequency or suitable energy. It is a radiation. Whenever the radiation of the suitable energy falls on this photosensitive material like a cathode, and here electrons are emitted from this cathode. So that effect only we are calling as a photoelectric effect. When we applied a suitable potential difference, these electrons are collected by the anode. All the electrons are moving towards anode, and once if electrons are reaching the anode, so there is a flow of current. So this current can be called as photoelectric current, and this current is measured by using microammeter. So here the entire process can be called as the process of emission of electrons from the surface of the metal when radiation of a suitable frequency falls on this metal is called photoelectric effect. The electrons which are emitted from the metal are called photoelectrons. The metal which emits electrons is called photosensitive material, and due to the electrons there is a flow of current in the circuit. So the current flowing in the circuit is called photoelectric current, and the entire process we are calling as photoelectric effect. So here we have to study the experiment photoelectric effect by varying different intensities, or by varying different potential differences, or by varying frequencies, and what we can observe from the experiment we have to study. So what are the experimental observations? So we can write here, what are the experimental observations, or what are the experimental conclusions from the experiment. Generally what we observed we have to study here, experimental observations or experimental conclusions. Experimental observations of photoelectric effect. It is one of the important 5 marks question for PUC. Experimental observations. So sometimes they may ask what are experimental results or facts or conclusions, all meaning same only. Experimental observations or results or conclusions. What are experimental observations, results or conclusions of photoelectric effect? Here I am writing a short form PEE, that indicates a photoelectric effect. So from the experiment of what we observed means first point. So what scientists observed means as soon as the radiation falls on the metal plate, for example at 10 o'clock we sent the radiation to instant on the metal plate, but without any time lag or without any time gap, electrons are emitted from this metal surface. So that means there is no time lag between the incident of the light on the metal plate and the emission of electrons from the metal plate. So it is a sudden process. So there is no time lagging or no time gap. That's why one point you can write, photoelectric effect is an instantaneous process. Photoelectric effect is an instantaneous, means a sudden process. Instantaneous process. So what does it mean? Photoelectric effect is an instantaneous process, means as soon as the radiation falls on the metal plate, immediately electrons are emitted from the metal plate. So there is no time lag between the incident of the light and emission of electrons. Hence, it is called as instantaneous process. Generally, very small time lag or gap is there. How much time lag means 10 to the power of minus 9 seconds. So almost negligible. So t is approximately equal to 10 to the power of 9 seconds. Correct. We cannot imagine also very small interval of time. Means for the light falling on the metal plate and emission of electrons, how much time is there? 10 power minus 9 seconds and almost negligible. That's why we can call it is an instantaneous process. That is. And second, one more observation. What happens when we are changing the intensity of the light? Whenever the intensity of the radiation changes, how the current will come outside or how the electrons will come outside, we have to discuss. So that is second, effect of intensity of incident radiation, effect of intensity of incident radiation on photoelectric current. Effect of the intensity of the incident radiation on photoelectric current. How the current varied by changing the intensity of the light. That you have to study. So here if you want to study this observation, so first only we have to take the relation between intensity and photocurrent. Remaining all the parameters must be kept constant. That means throughout the experiment we have to use only one metal. That means the metal is kept constant, and throughout the experiment only we have to apply a suitable constant voltage. So we should not change the voltage also, potential difference also, and also frequency also kept constant. But what we are going to change? Only intensity of the light. Whenever the intensity of the light changes and how the current changes, we have to study. So generally what is the intensity means? Here intensity of the light is equal to amount of energy transmitted per unit area per unit time. It is general intensity, meaning the amount of light energy transmitted per unit area per unit time is called as intensity of the light. And one more formula, intensity of the light is always inversely proportional to square of the distance. For example, it is an electric bulb, ultraviolet lamp, and it is emitting ultraviolet light. It is for example a screen or metal plate I am taking. Whenever the bulb is kept constant and metal also fixed, and there is no change of the distance, so no change of intensity of the light. Whenever this bulb is taken towards the metal, what will be happen? Distance decreases and the intensity of the light square times increases. So we are getting a more and more intensity of the light, but a metal is kept fixed. And when I am taking ultraviolet lamp far away from this metal, then what will be happen? Distance increases and the intensity of the light falling on the metal decreases. That's why always intensity of the light and the distance both are inversely proportional. Now how we are going to change the intensity? By varying the distance of this ultraviolet lamp and the metal, we can automatically change the intensity of the light. So by keeping the metal fixed and also frequency of the radiation fixed and applied voltage also kept constant, only we have to vary the intensity of the light, how the current changes. What experiment observed means photoelectric current. Photoelectric current is directly proportional to the intensity of the light. Whenever the intensity of the light increased, then what will be happen? Photocurrent also increases. More the intensity of the light, more the number of electrons coming outside, and more the photoelectric current. So photoelectric current is directly proportional to the intensity of incident radiation. It is second observation. Photoelectric current is directly proportional to the intensity of incident radiation. More the intensity of the light, we will get the more amount of current. And if you draw a simple graph, how we will get this graph? A graph is drawn by taking intensity of the light on x-axis. On x-axis I am taking intensity of the radiation. So intensity of radiation will be taken on x-axis. I am using a capital I. And a photoelectric current, I am writing a PEC, photoelectric current, on y-axis. What is the nature of the graph? For example, when intensity of the light is equal to 0, no electrons emitted, no current passes. So starting we have to take origin. as the intensity of the light steps wise increases and the current also gradually increases. So the nature of the graph is a straight line passing through origin. So it is a intensity and a photoelectric current relation. So it is a second observation. So first observation, photoelectric effect is an instantaneous process, and the second observation, as the intensity of the incident radiation increases, the photocurrent also increases. So photoelectric current is directly proportional to the intensity of incident radiation. The graph is drawn by taking intensity on x-axis and the photoelectric current on y-axis. Nature of the graph is a straight line passing through origin. That is second observation. And the third observation, how the photoelectric current changes with the change of the applied voltage. As a potential difference changes and how the current changes, we have to study. So that is a third observation. All right. Effect of applied voltage. Third observation, effect of applied voltage on photoelectric current. So third one, effect of applied voltage or applied potential. Effect of the applied potential on photoelectric current. Effect of the applied potential on the photoelectric current. So I think you have taken this one, correct. Now in this third observation, what are the parameters to be kept constant? So we have to study the relation between the photoelectric current and applied voltage. So remaining all the parameters must be kept constant. What are the parameters? Throughout the experiment, we have to use only one metal. For example, if you want to select a cesium, we should not change. So metal should be kept constant. And one more, intensity of the light should be kept constant. How we can keep the intensity of the light constant? The bulb, whatever the bulb or whatever the source of light you are using, it must be fixed at a particular place. Whenever the source is kept constant and the intensity of the light is fixed, and whenever same metal we are using, so metal also fixed, and only we have to change the applied voltage, like a 10 volt, 20 volt, 30 volt, 40 volt. As applied voltage changes, how the current varied, we have to study. That is third observation. So effect of the applied potential on photoelectric current. For example, starting the potential, the total circuit is completed, and I am applying only a 0 voltage. Don't copy this one. I am applying only, for example, 0 volt. Whenever 0 volt applied means, what is the current? 0 volt applied means the radiation falls on the metal plate. Electrons are emitted, but because there is no potential difference, we are not applying. That's why electron cannot reach the anode and no current passing in the circuit. So photoelectric current I is equal to 0, you should write. Whenever no voltage applied, no current. Now I am applying a potential difference of 5 volt. Then what will be happen? There is a potential difference between the cathode and anode, and electrons are attracted by anode, and there is a flow of current in the circuit. For example, current flowing in the circuit is equal to 2 microampere. Next, this value increases to 10 volt, plus 5 and plus 10. Here current also increases to, for example, 4 microamperes. So also value increases. Whenever this value, for example, increases to 15 volt, and what we observed means, so this value also 4 microampere. Whenever this value changes to 20 volt and also it is equal to 4 microampere, what we can observe from this data? As applied voltage increases, beginning of photocurrent also increases, and at a certain level it reaches saturation and a constant value. So this current can be called as saturation current. So as the positive potential of the anode gradually increases, the photocurrent also increases and becomes a maximum at a certain positive potential. So this maximum value of the photoelectric current is called as saturation current. Now steps wise I want to decrease the potential. What will be happened? So it becomes 20 becomes 15, 10, 5 and 0. So this current also gradually decreases. But whenever a potential of the anode is made 0, but a current may not be 0. So because, for example, when we are moving on a bike, and a bike moving with 70 kilometer per hour on the road. Suddenly the engine is, for example, seized off or switched off, for example, but a bike suddenly will not come to rest. So because of the velocity of the bike, and the bike will go some distance, and then it will be stopped. So same manner here also, whenever the potential of anode is equal, for example, 20 volt, and electrons are coming outside with a higher speed, they are traveling from cathode to anode. Suddenly whenever potential of anode is made zero, but some of electrons may not be stopped. So because of their velocity, they are moving towards anode. So that means when positive potential of anode is equal to zero in the reverse direction, and the current is not zero, something current flowing through the circuit. When I am applying minus 5 volt, so here for example this becomes 1 microampere is there. It is equal to minus 5 volt. So this value becomes 0.5 microampere. When this value is equal to minus 10 volt, it is equal to 0.2 microampere. Whenever this value is equal to minus 15 volt, and all the electrons will be stopped and current is equal to 0. So this particular minimum negative potential of anode is called stopping potential. So that means whenever positive potential of the anode increases, the current also increases and becomes maximum. So the maximum value of the photocurrent called saturation current. When a positive potential of anode gradually decreases, photocurrent also gradually decreases. And whenever potential of anode is zero, but current is not zero, because some of the electrons are still reaching the anode with some kinetic energy. And now with respect to cathode, we are applying a negative potential of the anode. So gradually we are increasing the negative potential of anode. At a particular negative potential of anode, all the electrons will be stopped without reaching anode, and then current become zero. So this minimum potential is called as stopping a potential or retarding a potential. So that is the effect of the applied voltage on photoelectric current. So here we can write what is a saturation current. What is meant by saturation current? Saturation current. The maximum value of photoelectric current. The maximum value of the photoelectric current. Maximum value of the photoelectric current at a particular positive potential of anode. Maximum value of the photoelectric current at a particular positive potential of anode is called saturation current. Saturation current. And one more, what is meant by stopping a potential? We are using the word stopping a potential. Stopping a potential. The minimum negative potential of anode. The minimum negative potential of anode. The minimum negative potential of anode at which the photoelectric current becomes zero. Minimum negative potential of anode at which the photoelectric current becomes zero is called stopping a potential or retarding a potential. Stopping a potential or retarding potential. Stopping a potential or retarding a potential. We can denote with symbol as V naught. V suffix not we are writing V naught. V naught. And from the experiment of what we observed, I'll draw one simple graph here. I'll draw a graph like this. By taking applied voltage on x-axis, whatever the potential we are applied will be taken on x-axis. It is origin. So it is applied voltage or applied potential. Applied voltage on x-axis. and the photoelectric current is taken on y-axis. On y-axis I am taking a photoelectric current I. So applied voltage is equal to V. So V taken on x-axis and the photoelectric current taken on y-axis. So here at a particular intensity of the light, the graph I am drawing like this. It is equal to saturation current. So observe this, the nature of the graph. It is equal to the intensity of the light I am taking I1. So it is equal, intensity of the light is equal I1. So check here, whenever the applied voltage gradually increases, the photo current also gradually increases and becomes a maximum. So which is called saturation current. So this current can be called as saturation current. When the applied voltage gradually decreases and the saturation here current also gradually decreases, whenever applied voltage is equal to 0 but current is not 0, and some of the electrons are still reaching the anode from the cathode. That's why there is something current. Now we are applying a reverse voltage like a -5, -10, -15 like this. At a particular minimum potential of the anode, the total photo current becomes 0. So this potential called as stopping a potential or retarding a potential. But one more, for example, intensity of the light is changed to I2. Whenever intensity of the light changed, saturation current also changes. Now we can draw the same graph like this. So the saturation current value changes, but observe this carefully. So here intensity of the light I1 and the current will be here, something value is there. Whenever the intensity of the light is equal I2, current also changes, but finally both the curves will touch at the same point. So that means stopping a potential does not depends upon the intensity of the light. It may be I1 or I2, whatever you may take, the stopping a potential is fixed. And for example, if take one more value I3, whenever the intensity of the light changes, but finally the curve reaches at the same positive same potential like I1, I2, I3. So intensity of the light different and the photo current also different in all the three cases, but in all the three cases the potential will be same. So from this what we can conclude, stopping a potential is independent of intensity of the radiation. So we can write that point, stopping a potential or retarding a potential. Stopping a potential is independent of stopping a potential is independent of intensity of incident radiation. Intensity of incident radiation, it does not depends upon the intensity of the radiation. Very important point. So sometimes theory questions may be asked, how the stopping of potential depends upon the intensity of the radiation, directly proportional, inversely proportional, or maybe inversely, or maybe directly, or independent. So stopping of potential does not depends upon the intensity of the light, it only depends upon the frequency of the light. So next point I'll give. So check this one. It is about the third observation, effect of the applied potential on photoelectric current. That is a simple graph also should draw like this. And the next one, effect of the frequency, effect of the applied so I think copied this one. I'll draw one more similar graph only. How the stopping of potential depends upon the frequency. So similar kind of the graph only I'll draw here. How it depends upon the frequency. So I think this one copied. How the stopping of potential depends upon the frequency of the incident radiation. So similar model I'll take applied voltage on x-axis and the photoelectric current will be taken on y-axis. On x-axis I am taking applied voltage or applied potential in a volt. will be taken on x-axis. On y-axis, I am taking a photoelectric current I will be taken on y-axis. So it is origin. Now first here in this case, I'll keep intensity of the light constant. So intensity of the light is kept constant, and I'll draw the graph for a particular frequency of the light nu 1. Here intensity of the light is equal I, and this current can be called as saturation current. So saturation current, as applied voltage gradually decreases, and this current also gradually decreases when applied voltage is made 0, but current is not 0. Whenever applied voltage is made negative, -5, -10, -15 something, at a particular negative potential of anode, photo current becomes 0. So that is called retarding potential or stopping potential. For example, here frequency of this light is equal to nu 1. Frequency of the radiation is equal to nu 1, and the stopping potential I am taking a V01. Now keeping the intensity of the light, only frequency of the light changes. Now we are observing the same graph like this. Check here, intensity of the light constant only, but the frequency of the light changes to nu 2. Whenever the frequency of the light changes, and the stopping potential also changes to V02, and with the same intensity of the light, again the frequency of the light changes like this. It is equal to nu 3, and stopping potential becomes V03. So from this graph we can observe one thing: the stopping potential only depends upon the frequency of the incident radiation, but not on the intensity of the radiation. That point also very important. So in this graph, frequency of the radiation nu 3 greater than nu 2 greater than nu 1. So nu 3 is higher than nu 2, and nu 2 is higher than nu 1. Same model, magnitude of the stopping potentials V03 is greater than V02 is greater than V01 is should write. So from this graph, from these two graphs, previous graph and this graph, we can understand on what factors the stopping potential depends. So we can say stopping potential depends upon stopping potential V0 depends upon frequency of the incident radiation, depends upon frequency means nu of incident radiation, frequency of the incident radiation. So we have to remember these 2 points carefully, on what factors the stopping potential depends and on what factor it is independent. That's important. So stopping potential is independent of the intensity of the radiation, but depends upon the frequency of the incident radiation. So these are important graphs both. So previous graph and this graph you have to learn carefully. Next, one more, fourth observation. Okay, right. Put the heading effect of frequency, effect of frequency on stopping potential, effect of frequency on stopping potential or kinetic energy of photoelectrons or Ke of photoelectrons, stopping potential or Ke of photoelectrons. I think this point also noted. So effect of the frequency, fourth observation will write effect of frequency of incident radiation on stopping a potential or maximum Ke of photoelectrons. Maximum Ke of photoelectrons. For this, one interesting thing you have to understand carefully. For example, I'll select a simple tank like this. One overhead tank I am choosing like this. It is at a certain level from the ground. The overhead tank is at certain height from the ground level. I am choosing like this. So it is a tank. And to get the water outside, there is a small opening here like a tap. Here there is a tap also like this. For example, the tank contains water up to here. It is the level of the water in the tank. So check here, if you observe carefully, the water in the tank is below the tap level. The water in the tank is below the tap level. Now, whenever I am open the tap, then what will be happen? No water will come outside because the water is below the tap level. And more I am opening the tap, then also water will not come outside. If you remove the tap completely, also water will not come outside because the water is below the level of the pipe. That's why no water will come outside. Now, for example, whenever I am maintaining the water above the level of the pipe, then so the water level is above the pipe I am maintaining like this. Now, slowly I am opening the tap. Water will come outside. More and more the tap opened, more the water will come outside. So, same manner, we have to observe this very carefully. For example, whenever a radiation of sudden intensity falls on the metal plate, but here when it is equal to frequency is equal to less than required frequency. For example, frequency equal to very less value. Required value is equal to, for example, 100 hertz. But I am supplying a frequency equal to only 10 hertz. Then what will be happen? Required frequency for emission of electrons equal 100, minimum 100 required, but I am supplying only 10 hertz. No electrons will come outside. And I am applying, for example, 50 hertz, then no electrons will come outside. And I am applying 99 hertz, also no electrons will come outside. Whenever the frequency of the radiation equal to or greater than the required frequency, then only electrons will come outside. So similar to the tap. For example, whenever the water is below the pipe level, even if you open the tap more and more, no water will come outside. And here also below the required frequency, whatever the intensity of the light may instant, no electrons will come outside. So correct? Here also, whenever we are maintaining the level of the water above the pipe level, now if you open the tap more and more, water will come outside more. Same manner, above this required frequency, when we are increasing the intensity of the light, more and more electrons will come outside and more current also passing in the circuit. That's why for the photoelectric emission, there is a minimum frequency required. So that minimum frequency can be called as threshold frequency. So the minimum frequency required for emission of the photoelectrons from the metal plate is called threshold frequency. So compulsory for emission of electrons, whatever the intensity of the light may be. So there is a minimum frequency required for emission of photoelectrons. This minimum frequency called as threshold frequency. That's important. So there exists a minimum frequency. There exists a minimum frequency below which there exists a minimum frequency below which no photoelectrons are emitted. There exists a minimum frequency below which no photoelectrons are emitted. Below which no photoelectrons are emitted. This minimum frequency is called threshold frequency. There exists a minimum frequency below which no photoelectrons are emitted. This minimum frequency is called threshold frequency. So we can denote with the symbol as nu naught. Threshold frequency nu naught. But above this threshold frequency, electrons will come outside. But below this threshold frequency, whatever the intensity of the light, no electrons will come outside and no current also passes. But one more we can write here. We have one formula, nu is equal to c by lambda, or lambda is equal to, there is a formula c by nu, where c is equal to speed of the light or speed of the photon, and nu is equal to frequency, lambda is equal to wavelength. Whenever frequency is equal to, for example, I am writing a nu naught, and wavelength we can write a lambda naught. So how lambda and nu related? Inversely proportional. So we are saying a minimum frequency below which no electrons are emitted, call it threshold frequency. But whenever frequency is a minimum, what about wavelength value? Maximum, inversely proportional both. So there exists a maximum wavelength above which no electrons are emitted. For example, for this particular metal, the required wavelength is equal to 5000 angstrom unit. The required value is equal, for example, 5000 angstrom, and for 5000 angstrom, electrons will come outside. But I am applying 6000 angstrom. What will be happen? No electrons will come outside. It is only highest value. So there is a maximum wavelength above which no electrons are emitted. So there is a minimum frequency below which no electrons are emitted. For example, threshold frequency nu naught is equal to 100 Hz, for example. And below 100 Hz if you supply, then no electrons will come outside, and the maximum wavelength equal to 5000, and above 5000 also no electrons will come outside. So we can say this lambda naught is called threshold wavelength. We can write here threshold wavelength. Threshold wavelength, the maximum wavelength, the maximum wavelength. Here maximum wavelength means maximum wavelength of incident radiation, nothing but the maximum wavelength above which, maximum wavelength above which no photoelectrons are emitted. The maximum wavelength above which no photoelectrons are emitted is known as threshold wavelength. But how both will be related means we can write the formula like this. Maximum wavelength above which no photoelectrons are emitted is called threshold wavelength. and more the speed of the photoelectrons, more the kinetic energy of electrons means more retarding potential has to be applied or more stopping potential has to be applied to stop the electrons. So that means maximum kinetic energy and maximum speed of the photoelectrons and also stopping potential depends upon frequency of the radiation, but not on intensity of the radiation. More the kinetic energy of the photoelectrons, if electrons are coming with the more kinetic energy or more speed, if you want to stop the photoelectrons, more work has to be done. That's why then only electrons can be stopped. So we can write here maximum kinetic energy of the photoelectrons must be equal to maximum work should be done to stop the photoelectrons. So here kinetic energy of the photoelectrons we can write the formula half m into v square, where m is equal to mass of the electron and v is equal to speed of the electron, speed of the electron. And here w is equal to stopping the potential v naught into charge of the electron is right. So note down this formula also important.